So, first of all, thanks for those of you, a few of you showed up at the office hours yesterday on Slack. I'm going to update the website, but we'll probably just do the Slack if it's okay with you, just because it's easier for me. And I assume it's pretty easy for you, so you can just type in your question. But if you really want to talk, of course, we can also talk, but I can jump on Zoom, but Slack is a little bit easier. So I'll stick to that from now on. So we'll do it every Wednesday, 6 to 7. Of course, if you have any questions along the way, you can just post it on Slack and I can answer it anytime. So you don't have to wait till Wednesdays, just to be clear. Okay, so let's pick up where we left off. We talked about improving solar cookers, and this was the next slide, which basically is what we call a Fresnel lens cooker. Of course, Fresnel lenses are flat lenses, and you probably have seen these Fresnel lenses used in flat TVs and things like that. Let's see. It's hard for me to monitor the chat, so if you want to ask something, I suggest you just talk, I guess. Easier. Okay. The idea that a Fresnel lens cooker is similar to the parabolic cooker. So if you recall, we had this where you were focusing all the light to the focus of the parabola, which we'll talk about later. Here, the Fresnel lens does the same thing in transmission. So here it's in reflection, it's like a mirror, but here it's in transmission. That's the only difference. So sometimes this is easier to do than the other. So otherwise, the specifications are roughly the same. You can get very high temperatures very quickly. It cooks quickly. You need to track the sun again, just like the parabolic cooker. It's relatively complex. I wouldn't call it expensive. These things are relatively cheap nowadays, but there's risk of fires and eye injury. So I want to spend about 5 minutes or so talking about some basic heat principles to when we try to consider some of the technical challenges involved in solar cookers. So let's see. Can we use a thermoelectric generator instead of battery for rotating the motor? Yes, I believe so. Anything that can generate power, but that's a good question. Okay, so the first thing, of course, in a solar cooker is we need to somehow achieve heat gain. We do this with a greenhouse effect. So essentially, sunlight comes through, the visible light, which is light photons with energy higher than infrared, passes through this transparent cover and gets absorbed by this dark pot in this case. Of course, when something absorbs light, it also re-radiates. This is a black body. You've learned this in high school physics. So this re-radiation happens at longer wavelengths, infrared. So visible will be shorter wavelength, higher energy. Infrared will be longer wavelengths, lower energy. We'll talk more about this as we go along. This infrared radiation is then trapped inside because it doesn't penetrate or transmit through this glass or plastic cover on top, which is transparent to visible light, but not transparent to infrared light. So the infrared light is trapped, and that causes this greenhouse gas effect, which of course we all know is what happens to the entire planet with CO2 and other gases, which trap the infrared light. So in this case, this is a beneficial property. We take advantage of that to build up heat inside this chamber, and the pot and the food is cooked efficiently. The other thing that's important is how is the light entering the system. This can be thought of as heat gain, where the energy is entering this closed system, and the orientation of the glass is important. So if we consider these two situations, one question I can ask you is which box will receive more sunlight? And if we were in a class, we would talk about this. I would ask you to discuss, but I think in the interest of time, and probably it's a little too simple for you, I would assume you all know that the box 2 will receive more sunlight just because it has a high. So the way you should think about this problem is that the amount of light that's entering the system is defined by the aperture of the system, right? So that's the aperture of the system. Now, of course, there's an angle between the ray of light coming in to the aperture. So you have to project the aperture to be perpendicular to the ray, which will be this line right here, okay? And that will give you essentially a cosine theta factor. And that was the area that is collected relative to the box here. And if you correct for that by actually putting in an aperture here, you're essentially collecting more light just because you're avoiding the cos theta factor. So you can kind of see this in this picture. Now, I can also ask the question, the gain is only one aspect of it. You're also losing heat. So if I were to ask, okay, which box has more losses, that's a bit more of a subtle question, because now you have to think about how is this solar cooker losing energy. It can lose energy by radiating heat out. It can lose energy by conduction, like this box is somehow touching something else which can conduct the heat out, or it can lose energy by convection. So there's gas molecules that touch this hot surface and take the heat away. And we'll talk about all three later on. But here, as you can imagine, because the surface area is much larger here, one would expect the box 2 to be have higher losses. It'll lose more energy. So when you think about a design, it's important to not just consider the heat gain, which is the amount of power coming into the system, but also the heat loss. So box 2 has higher heat gain. It also has higher heat loss. So when you do a design, you need to compromise these two, right? Somehow come up with the best possible design. So something to keep in mind. You can also add reflectors to enhance the heat gain. So which is here, there is no reflector. The entire box is increased in volume. Here you add a mirror, for instance, or a silvered surface like an aluminum foil or something like that on one side. It will reflect the light in. So here, the way to think about this is this is the physical aperture of the system. By placing a reflector, you're essentially increasing the let's call it a virtual aperture of the system. So you're essentially getting more of the light to come in, right? So that's a little bit obvious if you think about it. And I can put 2 of these and get even more of the light to come in and so on. So the reflectors essentially increase the effective light capture area of the aperture, okay? I want to take, well, I'm going to leave this as a homework problem because we have a lot of ground to cover. So one of the brainstorming questions is, think about this concept here where you are essentially applying very simple optics like mirrors. It's just a reflective surface to enhance the amount of light you're collecting. Are there ways you can come up with to increase this gain? Okay, I will leave this as a optional homework problem for you to think about. As I said before, the loss of the system is also very critical. So we have to think about the mechanisms, and there are 3 as we talked about. There's conduction. So the way you might lose heat by conduction is because you see this pot is sitting on a plate here, and that's touching the pot. So it's going to conduct some of the heat onto this plate, and if this insulation is not very good, it can conduct it out of the system. So that's conduction, is when things are in contact, right? So the absorber plate has to be well insulated from the bottom of the cooker here, for instance, to prevent that conduction loss to happen. Now you can also have radiation, which is the radiant heat, which is basically these wavy arrows showing photons of light in the infrared light. So this invisible light, you may not see it, but you can feel it, which is, for instance, if you sit close to the fireplace in the winter, you feel the heat, even though you're not touching the fire. And that's essentially photons of infrared light coming to you, right? So exactly the same manner, the pot will lose also infrared photons as well, and it can lose through the system. Of course, heated air, which is, of course, this is not a vacuum, so there's air here that gets hot and it will circulate. If there are leaks in the system, this is not a perfect seal. Some of that heated air can escape, and that will take the heat away, heat energy out of the system, and that's referred to as convection. So all of these are very, very important when you start thinking about designing such systems. Of course, it's a very simple example, but you should always keep in mind that the simple example is equally, the concept we are learning in terms of heat gain, heat loss are equally applicable to more complex examples like concentrated solar photovoltaics, for example. We'll see this later on. But I want you to get this picture for a simple example first. Heat storage, of course, we know is important for solar cooking because we want to be able to cook when the sky gets cloudy, or if it goes past sunset or whatever, right? So in this case, there's something called thermal mass, which is a mass that that can retain heat. Thermal mass is the ability to retain heat. So the pot has thermal mass. The insulation also has thermal mass, but you really don't want to waste your heat heating up the insulation. So you want to make sure that the thermal mass of the pot is much higher than anything else that is accepting the energy, in this case from light. So higher thermal mass also takes longer to heat up, so it takes a long time, but it will retain the heat longer. We all know this, so if you have gone to the beach in the summer, during the day, the water will warm up, and it can stay much warmer even in the evening, even though it starts cooling down in the air. So the air will lose the heat much faster than water. So the ocean will be much warmer than the actual air outside, right? So we have all experienced this. It just means that water has a higher thermal mass than air. The last thing I want you to think about are materials requirements. Again, this is a very simple example, but all these concepts are equally applicable to more complex systems. So that's why I want you to think about it, even though this might seem trivial. Of course, there are different ways to think about materials. One is structural materials. How do you hold the whole thing together? Can it be heavy? Do you need it to be super light? Do you need it to be resistant to water, humidity, other weather conditions, snow, whatever, right? So there are lots of options here. The other thing is insulation. Of course, how are you going to insulate the outside, whatever's inside the solar cooker from the outside world? It cannot be very expensive, and so on and so forth. Right? Is it locally available, for example? Transparent material on the top here, you want it to be transparent to visible, but you still want to retain the infrared light. And there are lots of cheap options. Glass might be too heavy, so you don't want to use it. So you might want to use plastics and things like that. Of course, moisture resistance is very important, because if you're talking about cooking, everything that humans eat that you try to cook will emit water vapor. So there will be moisture condensing inside this chamber. So you have to make sure that that doesn't affect whatever material that you're using. So all of these, of course, is a highly interdisciplinary problem, right? So as an engineer, you cannot just think about optics by itself. All these other things have to be considered in addition to cost and consumer preferences and whatnot, when you do this kinds of when you really want to make something that you want to be adopted by the world. And there are, of course, other considerations which might be outside technical consideration, things like size. Is it big enough for the amount of food? Is it for a village? If it's for a small family, is it portable? Are you going to use it for when you go hiking? Are there certain types of cooking utensils or vessels that need to fit inside? So all of these things also have to be taken into account. And when you do the design of such a system. Sunlight collection area, do you have lots of area? Are you out in the desert? So can you put a collector, for instance? Things like that. The other few questions, again, for you to think about are, is a square box better than a rectangular box? So actually, I'm going to break everyone into some breakout rooms and have you discuss these questions. These are useful questions to think about. Is a square box better than a rectangular box? If it's a rectangular box, which direction should it be oriented? What about tracking? What is the effect of tracking in this situation? And in this case, when I say a box, I'm talking about a solar box cooker. So let's take a minute, about 2 minutes, let's say 1 to 2 minutes. And I want you to discuss internally. I'm going to put you all in breakout rooms. There's 19 of you, so probably, let's see, whoops. Let's see, how many rooms? 19, let's say 4 or 5. Open all rooms. It will be random, so, okay. Just 2 minutes. Okay, you're back in the main room.
Oh, yeah, sorry. So the idea is to continue on the break room and discuss that. I'm sorry.
Well, I wish we had a lot of time, and I agree. A lot of these discussions are very useful, but I need to cover a lot of things today because we have to pick project topics and teams by next Tuesday.
Right.
So, but I do have a suggestion. That's what Slack is for. So for those of you who really want to explore some of these discussions, and I highly encourage you, just do a discussion on Slack. It's very easy. It's just a chat app, right?
Right.
Okay, there's a few more people. Okay, I think everyone's here. So I heard a few interesting comments, which was good. And I'm not going to ask you because I'm first of all, I'm very glad to hear that everyone was talking. So this is first of all, very important, especially in a remote situation, because many of you are first-year grad students or starting out. So I'm hoping that it's very hard to make these personal connections. So this is probably the small thing we can do where you can network, okay? So hopefully folks with similar research interests and so on. So I'm glad that everyone's talking, and please try to make the effort. The second thing I want to say is that I heard some really nice ideas and points, and I'll just quickly summarize what I heard. So I'm very excited to know that you're thinking carefully through these. One, someone mentioned, okay, maybe there was a question, is the area of the square box same as a rectangular box? Obviously, I didn't say anything because I want you to think through it. So, of course, let's assume it's the same. If it's the same, then what is the question? If it's not the same, of course, you would pick the larger box to a big extent, assuming that you can live with the losses, okay? So let's assume it's the same for the sake of simplicity. Now, someone had a really interesting point that if you had a rectangular box, you could align it in the direction in which the sun is going, right? So remember, during the day, the sun goes in a plane, right, in an arc, and we'll talk about it more. Sorry, I was moving my hand up here, but I realized you can't see it. So moving like an arc, but the arc is tilted relative to the Earth's surface. So, I mean, if you can put a rectangle, then you don't need to follow the sun. The sun will still be more or less pointing into the rectangle for a longer portion of the day. Now, of course, it would be nice if you could tilt it in the opposite axis based on seasons. So in the summer, it'll be here, winter will be here, and so on and so forth. Anyway, so we'll talk more about this later on.
I'm sorry to interrupt. There's a note in the chat.
Yeah, go ahead.
From Ekota. I think her connection is unstable or something.
Can
anyone do to improve that?
So does anyone else have problem? At least I'm on campus Wi-Fi, so I think it should.
No, I can hear you well.
Okay, so
I can hear you pretty well.
Oh, yeah, by the way, when I go home, this might change because my Wi-Fi at home is not great. So if you have problems, just tell me. I'm gonna try to plug into my home Ethernet, so it should be fine. But Ekata, my suggestion is to try to reconnect or restart your modem. If you still have problems, certainly turn off the video. Then I can try to help you troubleshoot after. So the next question about the orientation, of course, I just answered it because it depends on the axis in which the sun is moving. And is tracking required? Of course, if you can do tracking, it's always better because you'll collect more light because you're avoiding something called the cosine theta error, right? So there's a surface that you're trying to, which is, let's say, my hand here, that you're trying to collect the sunlight on, and this hand here represents the rays of light. If the rays of light are moving like that, it's going to form an angle. And you want to avoid that angle. You want to keep it 90 degrees all the time, which means that you want to track. And we'll understand this more mathematically later on. Okay, so the last point is that we also need to think very carefully as technologists. It's important we think about other things as well. Things like, okay, does the food actually taste good? Right? If it doesn't taste good, then no one will use it. So that's a very important point, right? But as an engineer, I didn't think about this, right? But obviously, if I had used it and I hated the food, I would never use it again. So it's obvious. Temperature control, someone mentioned last time, so that's obvious. What about cloudy days, cost? Now, disrupting traditional gender roles is a very important point, actually. The only reason I'm pointing this out is because solar cookers are very common technologies that non-governmental agencies try to deploy around the world in developing countries. And unfortunately, what happens is that it also tends to cause cultural shifts, because now traditionally the women are the one who cook. So if you allow them to free them from cooking, and the cooking is done automatically, for instance, solar cooker, that disrupts these traditional gender roles, which can be a great thing, right? Of course, it gives you gender parity and so on, but of course it is a problematic thing in many cultures and so on. So this is not something as engineers we think through carefully. So I'm just pointing this out as something very interesting that I never thought about, but something we should think about if we really want this to be widely adopted. On the flip side, of course, there are huge opportunities for us as engineers. There are new market opportunities as fuel prices rise. Think about ways to combine these technologies with when I say these technologies, I don't mean just a solar cooker, but whatever you develop with things like microcredits or innovations in economics and so on. And I'll come back to this again and again. Think about what Uber did to the taxi industry, right? Really, Uber is the largest taxi company in the world, but it doesn't own a single car, right? It changed the business model. Of course, it was backed by technology, but it changed the business model. So as engineers and technologists, we should also be open to the idea that the entire business model can also be changed, right? So keep that in mind. Airbnb would be the other example. Okay, let's move on to today's actual lecture. So
just wondering, what is microcredits?
Oh, yes, great question. So I'm not an economist, but I'll give you my naive understanding. Very, very, very small loans provided typically by the non-governmental organizations to small villages and artisans and so on. And the idea is that allows folks to be entrepreneurial, start their own companies and so on, and create jobs, produce economic activity, and then they pay back the loan. Typically, the loan is at a lower interest rate. It's a relatively small amount, and it may be forgiven and so on. One example that I've seen this work very nicely in Africa, for instance, is where microcredit people have used microcredit, for instance, to purchase small solar panels, and then they use it. Then they have a business where they use the solar panels to charge cell phones. So in many places like Africa, there's not enough infrastructure, so cell phones are basically the backbone of the economy, and making payments and so on. So everyone needs charging. There's no electricity, so you have this need where people need to charge their phones. So someone has a small business where they put a little solar charger and charge something. I mean, they charge a price for someone to charge your phone. So that's an example. Very small projects is what it comes to.
Okay, cool. Thanks.
Sure. Yeah. I should start going faster. So today I want to talk about other ideas as well. Okay, a few other projects. Now, again, what I'm going to present today doesn't mean you have to pick one of these. I'm just going to present this because these are things that I think are important for us to think about in this class. Okay, so don't feel pressured into picking some of these, but I want you to be aware of this. First is water. Water is probably the one of those things that we never think about or talk about, especially in this country. But around the world, this is a very important topic, right? 1 in 6 people on this planet have no access to clean water. Half of the hospital beds are filled with people suffering from water-related diseases. 80% of deaths in children are due to contaminated water. I mean, these are incredible statistics, right? So really, really important and big problem. What can we do about it? We'll talk about 2 different things: solar water pasteurization and solar desalination. Let's talk about pasteurization first, okay? What can we do to clean water? So water is dirty, we have to clean it. So you can heat water to about 65 degrees Celsius, 149 degrees Fahrenheit, which will pasteurize the water. What does that mean? It kills the vast majority of disease-causing microbes, something like 99.99%, okay? Now, there's also a time involved, so you need to heat this for a certain amount of time, which I forget, it's like, oh yeah, it says 60 seconds there. So it says, 99.999% of bacteria in water can be killed at 65 degrees Celsius in 60 seconds. Pasteurization is, of course, used very commonly in the dairy industry for milk. So they use moderate heat to kill disease microbes. In the case of milk, it's 71 Celsius for 15 seconds. So let me stop here, and I'm going to ask you a simple question. And I'm not going to break you into a breakout room, so you can just speak out. What problem do you see right away with this solution? So this is a solution to poor water quality, right? What problem do you see? Why isn't everyone doing it? I mean, there are many problems you can see, but say a few.
It's energy consuming, I guess.
Yes, that's good.
Yeah, not everyone has access to warm the water. I mean,
yes, good point. Yeah.
It's a great thing, but not everyone has access to it.
Yeah. Anything else? Yeah, this is very good.
And then you need to cool it down.
Oh,
And
sorry.
you need to cool it down as well, so you need
to drink it. Yes, good point. Yes. Anything else?
I would assume it'd be hard to maintain a consistent temperature of 65 degrees if you're doing large volumes of water. It seems like something that would work best with smaller volumes.
Yes, good point as well.
Yeah, proper temperature is in the chat from Ekata.
Okay, good. Yeah, so I think you guys are on the right track. But let me ask you a little bit of a common sense question. How do you know when you've reached 65 degrees?
A thermometer, but not many people have access to one.
Exactly. Okay. So this is a problem, by the way, I did not think of myself either, but if you were a poor person in a developing country, you don't have access to water, and if I tell them to do this, that would be probably the first question, right? How do I know that it's hot enough, it's long enough, right? So I'm going to show you a very simple solution that someone came up with to this problem. Again, think of this as a paradigm, an example for the way I want you to think. It has nothing to do with optics, but I'm just going to point out as a solution. So let's, it's called water pasteurization indicator. So I have to now play a video. So let me open up the video, hold on. There we go. So I'm going to turn up the volume because you could hear it last time.
The WAPI, or Water Pasteurization Indicator, is a simple device that indicates when water has been fully pasteurized. A plastic vial with the wax on the top and the washer on the bottom is placed in the middle of the pan. When water is heated to the pasteurization point, the wax melts and drains to the bottom of the vial. When cooled, the wax hardens again, and the WAPI can be turned over and reused again and again.
Okay, so you guys see it's just a piece of wax, but it's engineered such that it will melt at that temperature. So it typically is colored, so it just becomes colorless. So you maintain it, and then you can reuse it. It's very cheap. It uses a washer to weigh it down, right? Very simple. This is the sort of innovation which can actually change the world, right? Because it's simple, cheap, everyone can use it. Okay, so let's go back to. And I personally like very simple things like this.
What about just boil it? Like, so you don't need to pay those extra attention buy extra measuring. You just boil the water. It's like a lot more straightforward.
Yeah, so this is a first world solution. Think about how much fuel it takes to boil the water versus how much fuel it takes to heat it to 65 degrees. It's a big difference. So that means you need to have a lot more fuel in order to boil the water. So certainly that works, but it's overkill. It's very expensive, right? That's the way to think about it. Oh, I mean, it depends who you're talking to, obviously. But it's a good point. What other things can you do? Of course, you can use a solar cooker. And there's a custom device. So I'll play a couple more videos. Again, my goal here is just to give you a range of what people are already doing. So let's play the first one with simply using a solar cooker to get the water to be the temperature you want, which is very simple. Okay, you guys can see that, right? It's the same kind of a panel cooker. You put the water in the focal plane. You put the WAPI in there. So there's the WAPI. It's got a color in it, so it's easy to see. And when it melts, it just goes down. And you ensure that it stays down there for 60 seconds or whatever time you need it to. Now it's hot. Okay, so you get the idea. The other concept is perhaps even simpler. This is a very simple product called AquaPack. So I'll just play that.
Over
quickly.
1 billion people are exposed to biological pathogens in the water they drink. The AquaPack uses solar energy to kill these pathogens using the proven process of heat pasteurization. Simply fill the AquaPack with up to 4 liters of water, place in direct sunlight, and observe the orange water pasteurization indicator. After a few hours, the orange color disappears, indicating the pasteurization temperature has been reached and the water is safe to drink. The AquaPack can be inexpensively manufactured in developing countries for about $2 each, providing both jobs and safe drinking water.
Yeah, so you have that idea. There's an even simpler solution, and this is the last video I will show. Let me just play that. It's only a couple of seconds. It's actually interesting. And then maybe we can discuss. Oh, I don't have it here. Hold on, sorry. Let's see, it should be here somewhere. Okay, last one. It's 2 minutes.
I'm so thirsty.
Oh, no, don't do that. That water will make you ill. Yeah, she's right. I've got a better way.
By the way, hopefully it gives you some ideas when you do your own video.
Okay, blah, 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 blah. Just really easy, yeah, blah, blah, blah. You're just going there. No, it's not that complicated. Okay, it's really simple. You get a plastic bottle that's clear, fill it with water, and put it in the sun. How does it work? Well, the UV rays and the heat from the sun kill all the germs which make you ill and get you sick with diarrhea.
What equipment do we need?
Just a regular plastic bottle that you've cleaned out and filled with water. But how long does it take? Okay, you leave your bottle outside all day, and you can make it even quicker by using a shiny surface to reflect more light, or putting it somewhere dark to absorb more heat.
That sounds good.
There must be some disadvantages, you know. If the water's really cloudy, you might need to filter it first. If it's raining, just collect that water and use that instead.
Okay. I think I'll pass that. That's good enough. So you get an idea. So of course, you saw the simplest possible innovation in optics. They just put a reflective surface underneath it to collect more light. Now, of course, this is just a greenhouse effect as well, right? So same thing as what we talked about for solar cookers. Again, my goal here is for you to just think about simple ideas that you might dismiss at the beginning, but simple ideas tend to be quite powerful, especially if you explore them. So the two things that are happening here is temperature, but of course UV, that if it can pass through the plastic, can also kill the bacteria, especially under sunlight. So that's kind of nice to keep in mind. It's bad for many things. For instance, if you wear PET glasses like I do, these yellow over time because of the UV rays, because most polymers will absorb the UV rays and denature. Just like when you tan or, people get skin cancer. It's the same kind of principle. Okay. By the way, there is an interesting impact of UV on solar cells as well, which we'll talk about later on. So the second topic I want to talk about is solar water desalination. Of course, desalination is, what is the difference between desalination and pasteurization? Pasteurization means the water is already drinkable, except that it has bacteria and organic contaminants in it. So you want to kill it, so make it safe to drink. Desalination means you want to take water from the ocean which is, vast majority of the Earth's surface, and somehow clean it so we can drink it. Right? This is, of course, very important in places like Utah, where we will eventually run out of water. Places like Southern California, where they've already run out of water. So San Diego has one of the world's largest desalination plants in the world. Israel, lots of the Middle East and so on, right? They're already doing this. So it's a very important, important technology, important problem and important technology. So water scarcity and solar resource abundance coincide. In other words, sunlight again coincides is where there is less water, drinking water. So can we take advantage of this? That's really kind of the motivation. Now, of course, nature already does this for us, right? In the natural hydrologic cycle, it's a natural solar desalination. So water from the ocean evaporates up into the clouds. Clouds move in and, of course, condense into clouds and then move over land, and it gets, it becomes, falls down as water, again, fresh water. Now, this process, of course, leaves all the salt behind, and this water is drinkable now. So that's exactly the process we want to do in an artificial manner with high efficiency, hopefully. Okay, so everyone knows this. Now, there are many ways to do this. We want to remove salt from the water. We can use something called reverse osmosis. Now, this is the most commonly used technology today in industrial water desalination. So if you go to the plant in San Diego, for instance, this is what they'd use. And the idea is very simple. So imagine you have two cylinders connected by a membrane. This membrane is permeable to water, so that water can flow, but the salts cannot. So the pores of the membrane are small enough that the water molecules can flow, but it will prevent the salt from flowing through. So this is, the blue is salt solution. So if you don't do anything, the osmotic flow means water will flow from the clear side to the salty side, right? This is just pure diffusion. That's what we call osmotic flow. This is exactly what happens if you open a perfume bottle on one side of the room. Eventually, the perfume molecules will reach the other end of the room, right? We all learned this in undergraduate physics or high school physics for that matter. We want to do the opposite. We want to go the other way. So that means, so by the way, this occurs naturally, which already gives you a hint that this is obeying the laws of thermodynamics, because it obeys naturally, okay? So when you want to go opposite to thermodynamics, when you want to go against thermodynamics, you have to do some work, okay? So this is what's happening on this side, reverse osmosis. You need to put some pressure here, you need to push the water down here, so it will flow through the membrane to the other side, but the salt won't flow through. Salt is trapped, water flows through, and you get clean drinking water. It requires energy, okay? This is the second law of thermodynamics in action. We'll come back to this more in a little more rigor later on, but you get the idea. So I have a closed system. If I want to go against thermodynamics, I need to do some work on the system, okay? In this case, it's pressure. Now, of course, this is very energy intensive. So if most of the reverse osmosis plants require huge amounts of energy. So these are not very carbon neutral or not great for the climate. There is, of course, another environmental problem, which is that it ends up with lots of brine, which is very salty water, which you have to dispose of somehow, right? So that can cause environmental issues as well. Now, of course, one way to address this from a clean energy perspective is to produce this power from photovoltaics. So I'll show you one example of that, which is here. I'll play the video shortly, but the basic principle is that you use photovoltaics in a compressor. So you essentially have solar panels which follow the sun or whatever. Then you have some control electronics with a pump. So there's a pump which pushes the dirty water, salty water, through the membrane. Now, what's important is that pumps operate most efficiently when they're at a fixed speed. Unfortunately, photovoltaics do not produce fixed current because the sunlight, when it's cloudy and so on, it will shift, right? Because suddenly if a cloud passes overhead, the current will fall. So that's not great for a motor, but the motor cannot go up and down. You know, you don't want, when you drive your car, you don't want it to, you don't want to change speeds rapidly. You want to go at a steady speed, right, for very efficient operation. So for that purposes, you have some control electronics here. So and then they push it through the membrane system, which is shown here, and the fresh water is stored here. It can be fairly portable. It's useful for disaster relief. It turns out to be a controls problem. So for those of you electrical engineers, you can appreciate that this is a controls problem because you have to see how much power is coming from the panels. You want to make it match what is the ideal optimal operating point for a motor, right? You can think about other ways you can use optical engineering to help. You can think about how would you improve it. And I won't, at this point, break you into breakout rooms yet. We'll come back to this later on, but let me just check the chat to see if I'm, okay, I don't need to look at that. Let's see. Okay, so there is a, I guess I skipped that video, so that's fine. Let's keep going and we'll come back to that point. Great. Oh yes, I wanted to show this next. So there is another really interesting technology from Evelyn Wang's group at MIT that just was demonstrated like a month or two ago in the summer, this summer, where, let me zoom in here. So this is what the system looks like. Let me explain what's happening, okay? So you have sunlight coming in. You have a transparent insulator here, which is trapping the light. So basically trapping the heat, sorry. So this is basically like the greenhouse effect. You have a black heat absorbing material, which essentially absorbs the light and converts it into radiant heat. So it emits infrared light onto this wicking material. So very simple wicking material pulls up the dirty water, and then the water is heated up because of this radiant heat, and it evaporates and it condenses on some surface here and then flows down and you get clean water. Now what they did was very clever, was that when this water evaporates here, it is of course losing heat, right? When water evaporates and becomes steam, when water evaporates, it is absorbing heat. But when it condenses from steam to liquid, it's losing heat. So this is essentially giving out lots of heat. That heat is wasted in usual systems, okay? Here, they're using that heat in multiple stages that are vertically stacked, which you cannot see here. But I'll play a short, video just to illustrate this point. And that's the video of their system sitting on the roof of a building. So let me just play this two things. This is called a solar still, because it works not by the membrane method, but simply by evaporating the water, just like the natural hydrologic cycle. So in this example, oh, this is for the group in China as well, Shanghai Jietong. So here you can see the freshwater starting from the first stage, then the second stage, then the third stage, and so on. So you can see the light, sunlight, and the wicking material is here. Okay. And eventually all of them pass through, and if I play this, you can see this is the steady state, which means that all 10 stages that they have is producing water at a fixed rate. Of course, this is sped up as you can see. Now, you can also have very relatively low tech solar stills, and that's what this is, right? You can simply build a pond. They're called salinity gradient ponds. So simply you have salty water here. The high salt content brine gets hot and sinks to the bottom. Then the low salt content cool water remains on the top, and then you have a salt gradient in between, which acts as more or less like an insulator. And what happens is that then you can use this hot part of the brine to heat. So in this case, the hot brine is pumped through an evaporation system. The cold water passes through a condenser system. So you have an evaporator and a condenser. It basically acts like a refrigerator. So now you can run what's called a heat engine. So in this case, you have a working fluid which is getting hot here, and then going through the condenser, getting cold, and going through a cycle. So there's a hot region and a cold region. And as the liquid passes through this turbine, you can generate electricity, for example. So you potentially get clean water and electricity at the same time. Now, this is, of course, relatively low tech, and we'll talk more about this, this idea of the hot part and the cold part, because that's required by the thermodynamics for something called a heat engine, and we'll talk more about it later. The efficiency is relatively low, it's 10 to 15%. Both direct and diffuse sunlight can be absorbed. Direct means there are no clouds, diffuse means it's cloudy, and we'll talk in more detail about it in the next few lectures. Okay, so we saw this, I'm gonna skip that. You can also do this with a flat plate collector, where you simply have flat solar plate collectors to collect the light from the sun. So simply to heat up the liquid working fluid, essentially. So in this case, you can have many of these stacked here. It's low level heat is generated by the collector. Then you can essentially evaporate the water out of the brine and collect the clean water. I won't go through the details here, but it's basically the same system as we talked about before, slightly different configuration. Of course, you can speed this process up by using optics, and this is what we are interested in. The simple approach is to simply use a parabolic reflector, which concentrates light, just like in the case of the solar cooker, onto the focus. And the focus here is a tube which runs a working fluid, which can be water, and the water evaporates. You get the clean water. Yeah, or you can use some other liquid like ammonia or some other gas that you can then use to run a turbine to generate electricity. Here's a very large system, so you can see a person there for scale. Here, of course, you have to track, right? You have to track the sun but one interesting thing to note is that this is one-dimensional. It's a one-dimensional parabola. It's a slice of a parabola. So you only need to track in one axis. The other axis is degenerate, right? Nothing happens to the light, it's the same. Which means that you have to track during, I mean, if you align this axis along the motion of the axis of motion of the sun during the day, you don't need to track in that direction, but you can track in the seasonal direction. So winter to summer, okay? You'll see a lot of this later on, so. This is okay, so here's an interesting problem that I'm going to break you out into different rooms to discuss, okay? So let's go through this problem carefully so you can understand it. First of all, let's see what this is. This is called a single effect solar still. Very simple, okay? There's a brine solution. It is enclosed in a greenhouse with a tilted roof. Okay, it's a glass or plastic cover. Sunlight comes in, again, heats up this enclosure. You can have a reflector to increase the amount of sunlight, just like we saw in the case of the solar cooker. Dirty water inlet comes in here. Okay, that water gets heated up. It evaporates to the top. It condenses on the top surface, flows down because of the tilt, and then fresh water comes out. Okay, so that's the freshwater trough. Okay, so it's very simple, right? So now let's think about some simple concepts here. It's simple, inexpensive, but slow and useful for small amounts of water. Now let's try to understand what that means. The energy required to evaporate 1 kilogram of water at 30 degrees Celsius, let's say that's room temperature in the tropics, for example, is about 2.4 times 10 to the 6 joules. Okay, this is the amount of energy for 1 kilogram of water. What does that mean? Again, let's make sure we understand. If you have a kilogram of water, a weight of water as a liquid, the amount of energy that I have to expend in order to evaporate it, starting at 30 degrees, so I need to take it from 30 degrees to 100 degrees and allow it to evaporate. That amount of energy is 2.4 million joules, 2.4 megajoules, okay? I assume everyone knows the units and so on, right? Now, if the solar intensity we refer to as insolation, not insulation, insolation, and we'll talk more about it so you'll become very familiar with these terms, is 250 watts per meter squared. How much water can be produced per unit area per unit time? Okay, you can assume an average efficiency of 100% for this analysis, it's fine, but typical efficiency is 30 to 40%. Okay, if everyone has written this down or memorized it, I'm going to put you in breakout rooms where you can discuss a solution to this, okay? Just like I'm going to give you 2 minutes. So make sure you get the numbers, Okay, 1 kilogram is 2.4 megajoules. How much water can be produced if the sunlight is 250 watts per meter squared? How much water per unit area per unit time? So assume this area is 1 meter squared and assume 1 second or 1 hour or whatever, doesn't matter. Okay, here we go. Do the same rooms, okay. Some of these rooms are a little bigger, but okay. Okay, everyone's getting back slowly. So I'm gonna share my screen. Okay, so anyone want to venture an answer so far? No, no one.
So I think it will get about 0.1 gram of water per second per meter.
Okay. I don't know the answer, I suppose, but I think it's important. I want you to understand how to solve it, how to think through it. So let me see if this works, hopefully. So we know we need two. This is very slow. Never
You
mind.
can try the annotation maybe.
Yeah, I was trying, but it's too slow for my iPad. So let me close it. Sorry.
Yeah, it's not showing up properly.
Hold on, I gotta. we're working through technical issues.
Yeah, I mean,
Or you can open a Word document and just type it in a Word document.
Yeah, it's fine. I mean, I have a solution. I just need to do one thing. When I do an AirPlay to my iPad, it really slows down the computer, so I just need to disconnect it. Okay, let's see. Whoops, okay, we're back. So you can see this still, right? I hope.
Yes.
Well, it's still very slow, sorry. I don't know why. So I guess I'll just talk, we can just talk through it. So of course,
your slides are stuck, I think, or I don't know what you're doing.
yeah, I'm just putting this in place. I'm gonna hook up to the internet just in case that's the problem. But okay, so you can see you need 2.4 times 10 to 6 joules, and you're getting.
Hello, you got disconnected maybe?
Yeah, cut off a little bit.
I think, wait, I'll just text you on Slack. I think he got disconnected or something.
I'm still here. Can you hear me?
Just one.
Okay. Yeah.
Just
All right. Yeah.
so I felt the U Wi-Fi was better. So before you said you're gonna connect to your family Wi-Fi, that U Wi-Fi was actually more stable. You got stuck less.
Yeah. I'm on campus. I'm actually in my office. So
it's still the same.
in any case, let me just get to this. It's just my computer really slowed down when I connected to the iPad, which I should not do.
A lot of my other professors have been using Google Keep to just scribe notes. They just open another tab.
Ah, okay. I'll give that a shot. So you can see that this is watts per meter squared, simply joules per second per meter squared, right? So if you need to, if what you're getting is 250 joules per second per meter squared, and what you need is 2.4 times 10 to the 6 joules, then you can take 2.4 times 10 to the 6 joules divided by the rate at which you're getting that, right, which is 250 joules, sorry, slow, per second per meter squared. And you have to take the inverse of this, because eventually what you want is kilograms. Oops. So I forgot that this 2.4 is per kilogram, right? So what the answer you are looking for is how many kilograms can I get out of 1 meter squared per second. So you have to take the inverse of this, right? Then the joules cancel out, you'll get kilograms per meter squared per second. Okay, so essentially the amount of energy you need divided by the rate at which you're getting the energy, take the inverse of that, that will be the amount of water you're creating. But in any case, what you will see, as someone pointed out in the answer, is that that's a very small number. So even with pretty good sunlight, you can only get a tiny amount of water. So
what about the efficiency? I think it's 30% or 40%.
Yeah, so you have to multiply this by 1 over 30%. That's why I said in the beginning, you can just assume 100% efficiency for just.
Oh, sorry.
So in this class, we will do quite a bit of hand wavy math because we want to get a quantitative, a qualitative picture of what's happening. So I want you to understand, okay, is it a lot of water? Is it a little water? Is it medium-sized water? That kind of answer. Which, by the way, I should also make a quick point. So in the exams and in the exam, especially, even if you don't get the final answer right, it's much more important that you show how you approach the problem. Okay, which I think you know in most classes today, that's what you do. But just want you to be aware of that. Okay, so you can think of the materials are important in this kind of system because you're handling water and steam and so on, right? Many system design improvements are possible. You can also have different configurations. So this is a greenhouse-like configuration, exactly the same technology as before. Water just evaporates, condenses, collects in a trough here. I won't go through this, but the key challenge here is that the corrosion of the collector due to contact with saline water. So keep in mind that this water here is touching all these surfaces, and salt water, as we all know, can corrode surfaces. So you have to be aware of that when you do design of systems like this. You could also think about the humidification, dehumidification problem, which is related to this. So we'll just point this out. You can have a solar collector, which is collecting sunlight. Dry air comes in, and you pass it through a humidifier. Brine comes out in this example. So this is preheat. So in this case, there's preheated seawater going in here. Warm humid air is then passed to the dehumidifier, where the cold seawater comes in, the fresh condensate comes out, air comes out. So in this cycle repeats. So you can see the air is this red arrow, which goes through this cycle. This is the water arrows in green, follows this cycle, and the fresh water comes out here. Exactly the same principle, right? So you're simply heating up the water, you're condensing it and getting the fresh water out. So again, another way to think about this. So just to summarize what we have discussed so far, we've thought about solar desalination in two aspects. One is there's a direct sunlight, so simply use solar sunlight to create the distilled water, which is fresh at small scale, stills, etc. Or you can have indirect, where the solar is used to produce the energy. In the case of photovoltaics, for instance, and that energy is used to separate to operate something to to separate water from the brine, whether it's reverse osmosis or whether it's simply just heating the water. Right? Solar thermal, photovoltaics, humidification, dehumidification. So lots of options, right? In all of these, of course, you can apply optics, right? Because you're collecting light to do something. So optics is always can be applied to do something better. So that's where our role comes in as well. The next topic this is the third topic, I want to talk about is solar refrigeration, which is a little bit of, if you think about it, it's a little bit of a misnomer, right? In sunlight, things heat up. How do you cool things down? But you can imagine this is a very important problem, right? Because you want to keep food, medicine, things like that over long periods of time. One of the big challenges, for instance, with the COVID vaccine, for instance, is how do you deploy this around the world without, especially because flu vaccines, for instance, has to be refrigerated. So the COVID vaccine will have to be refrigerated, and we need to deploy it around the world. And lots of the world don't have access to electricity. So how do we solve it, right? It's a very, very pressing problem today. You can also think about, can we make ice and so on. So in order to really answer this question, we need to understand something called the vapor compression cooling, which is how our fridge works. And many of you probably already know it, but let's watch a quick video just to recap this concept. So I'm just gonna play that very quickly. So let me close this. Close that.
In this video, we will learn about refrigeration vapor compression cycle.
Just like pressure, yeah. You will see what happens. The liquid is compressed. So, sorry, the gas is compressed to become a liquid. So I'm going to speed this up a little bit.
Refrigeration means cooling of a system below its surrounding temperature. It is based on the concept of reverse heat engine cycle. A refrigerator maintains a temperature a few degrees above the freezing point of water. It consists of a thermally insulated compartment and a heat pump that transfers heat from the inside of the fridge to its external environment so that the inside of the fridge is cooled to a temperature below the ambient temperature of the room. As we will see, a refrigerator is made up of different components like the evaporator, a compressor, a cooling fan, and a condenser. The compressor compresses the refrigerant, which is ammonia gas, as shown in blue color, and as the gas is pressurized, it heats up, as shown in red. Cool air sucked in from surrounding passes over the condenser and becomes hot. The coils at the back of the refrigerator let the hot ammonia gas dissipate its heat, condensing pressurized hot ammonia gas into liquid. The high-pressure ammonia liquid flows and passes through the expansion valve, where it expands and the pressure is reduced.
So I should point out a quick point here, which is important. So here there's an expansion valve, which means that the liquid is expanding and becoming a gas. So when liquid becomes a gas, it's taking energy from the surroundings, right? The gas has more energy than the liquid. And when it takes energy from the surroundings, it cools the surroundings. So keep that point in mind.
And the pressure is reduced. From here, it moves to the evaporator, where it boils and vaporizes, whereby the chamber's temperature drops down to minus 27 degrees Fahrenheit. The ammonia gas is then sucked by the compressor, and the cycle repeats itself.
So let's come back to the... so you can kind of see what needs to happen. You need to have a compressor, you need to have a pump, and that's it. Those are the two areas where you need to expend energy, right? Everything else is natural. So you need to pump the liquid, then compress it, then allow the gas to expand. Sorry, allow the gas to expand. So that means you need two places where you need to put energy. So you can, of course, use photovoltaics to produce that energy. That's the obvious thing. So you can put a solar panel, use sunlight, run a DC motor, which does the compression. So here you can see the heat coming in to the evaporator, and the condenser, the heat is output to the ambient, and inside it's colder. Of course, here the challenges are, you might need grid connection because you want it to work at night, for instance, or you need a battery. The other thing is that, of course, like we talked about before, motors work most efficiently when they're at a fixed speed, rotational speed. In the case of sunlight, if you have cloudy days and so on, the motor speed can change rapidly, so it's not very efficient. So you need some control electronics there. The efficiencies are not great. They're about 30%, but they can be expensive. There are other approaches as well. One is based on thermoelectric cooling, which, by the way, this has nothing to do with solar, but I want you to be aware of it because thermoelectric cooling, for instance, is very important in space. So when you think about the Mars rover out in Mars, when you're in the Martian sunlight, it can get very, very, very hot, and you cannot run a compression engine, right? So you have to have a solid state, very lightweight refrigerator to keep the electronics cool, and this is how it's done. It's using a solid state device, essentially something called a Peltier effect, which takes an N-type semiconductor with a P-type semiconductor, which simply means, hopefully those of you who are electrical engineers know this, but N-type semiconductor has an excess of electrons. So P-type semiconductor has a vacancy of electrons, lack of electrons. So there are more electrons here. They flow in a certain fashion, so they release the heat on one side. So in this case, you apply a voltage. So the electrons flow to the negative terminal, pass through here, pass through the N-type, release the heat, and then come back. There's a connection here, comes back here, goes this way. So the holes flow the opposite way. Hole is an absence of electron. So this flow of the electron essentially means that the electron absorbs heat from one side of the Peltier device and rejects it on the other side. So just like we had the compressor and the condenser, the Peltier device has one region where it absorbs heat and the other region where the heat is released. Okay. So of course, but because there's no moving part here, this is completely solid state. So it's very small, portable, but relatively low efficiency and of course very, very expensive. But if you're sending something to space, you don't care about the cost, you care about the weight. So that's important. There are other technologies that we won't talk about too much. Solar thermal refrigeration, you can use the heat, solar heat rather than electricity directly. So this can be done in a variety of ways. For instance, with solar collectors running a fluid, then you can run a heat engine with it. Again, I won't talk in much detail about it, but basically we are going to think about heat as an input to the engine for cooling. Engine refers to like a compressor, anything that can do work, okay? There are many challenges here. One important thing to think about is the collector loses heat at higher temperatures, but cooling engine works better at higher temperatures, which we will see when we talk about thermodynamics. So these are two opposing requirements. So one, can work against the other. Whoops. So this is a thermomechanical refrigeration where, again, solar collector creates a hot region of the heat engine where this is the heat, the hot part of the engine, and this is the cold part of the engine, which is the ambient, and the difference is the work, which then is used to run a compressor. This is what's referred to as a heat engine. We'll talk much more about it next week, actually, the week after next. So I'll just quickly mention that. It's a relatively low efficiency, 10 to 15%, so something to be aware of. There are other approaches which not terribly important for us. I'm just leaving that for additional reading for you. It's less important for us. Oh, yes. So this is my last slide, and I want to make sure I have a few minutes to do a couple of polls. So this is just a simple idea that I floated a couple of years ago because we were thinking about how to have a personal device that can produce clean air during inversion in Salt Lake Valley. Excuse me. Could you have a hat which has a fan and a activated carbon filter, a HEPA filter, pulls dry air, dirty air in, pushes clean air out? And yeah, could it be lightweight with a very small fan, very small battery? Could it be solar powered and so on? So it's just a crazy idea. So you can also think about crazy ideas for your projects as well. So by the way, the whole purpose of today's lecture was just to give a quick survey to give you ideas on what you would like to work on as a team project. Again, this doesn't mean you have to pick any of these. I'm just giving you ideas to think about. And some of you already responded to my email, excuse me, about requests for team members and so on. So if you have preferences, please let me know. Okay, so the last few minutes, I want to run a couple of polls to, yes, so this is not an anonymous poll because I want to get some idea of what you are all interested in, okay? So you can answer that. And I won't post it. This is just for my purposes. And I think you can pick more than one. So maybe don't pick more than two, I would say.
Sorry, I think I somehow like canceled that little window. Do you mind send that again?
Yeah, sure. I'm gonna end it, so you're gonna have to do it again. Sorry.
Oh, sorry. I'm sorry.
I'm gonna send it again. Sorry, guys. Relaunch. And I think I also put in other. So if you have good ideas, put them in other, and you can message me later with what your idea is. And again, this doesn't mean I will be able to put you all on the project you picked, but I just want to get a general sense what you're interested in. Okay, a few more people. Three more people. Okay. Don't know if today, Apratim, I guess you don't have to, so.
Yeah, does it need me to?
No, you're good.
Yeah.
Perfect. So I won't, well, let me see. I guess I can share the results. It's anonymous, but you can see it. So most of you picked this. Wait, no one had others. That's surprising. Okay, think of your own ideas. Okay, last poll and then we'll end. Tell me a little bit about yourself, basically. What, okay, I'll just launch the poll. I was just trying to get a sense for what your background is. This is, I think, not anonymous either. Or maybe it is, I can't remember what I picked. But I would say talk about what you can say what you're interested in, but I was hoping to understand what, yeah, either way, what you're interested in or what you have some experience in the past. Great, we have a nice diversity. So my hope is to make teams that have a diverse background, but diverse points of view, because that you can come up with better solutions that way. One more. Okay, we're done. Great. Okay, I'm going to stop here. By the way, I can share the results. Great. We have lots of hands-on folks. That's fantastic. I hope you have a garage where you can make some stuff. Okay, I'm going to stop here and ask if there are any questions.